So this is going to be part 2 of the video lesson for section 8.4. In part 1 we talked about the product property of radicals, how to combine and break apart radicals that are where multiplication is taking place. In part 2 I'm going to cover quotient property of radicals and then sums and differences with radicals. So I'm going to start with the quotient property. So this deals with division within a radical, or when radicals are being divided against themselves. So for example, if I have the square root, and underneath the square root we have a divided by b. So this is a fraction, and in part 1 I told you that fractions was one of the no-no things to not have underneath the square root. So we can't have fractions underneath the square root. So what you can do when you encounter a fraction like this is break it up into two separate square roots. Square root of a divided by square root of b. So this is similar to how we break things up in the product property, except here we're doing it for division. So not a problem. Now you no longer have a fraction underneath the square root. Now you do have a square root in the denominator, which is another one of those no-nos, but we'll deal with that in just a little bit. So here's a problem numerically speaking with numbers in there. So an example that has numbers. 16 over 25. Again, it's a fraction underneath the square root. Can't have those, so let's break it up into two separate parts. Alright, good. Step 1 done. Now let's take a look at the individual square roots, or the individual radicals. In the numerator we have the square root of 16. 16 is a perfect square. The exponential form is 4 squared. In the denominator we have the root of 25. 25 is also a perfect square, conveniently, and that's a 5 squared in its exponential form. Just like before, you can cancel out the power of 2 with the square root and kind of liberate that base, so to speak. When you do that, you end up with 4 over 5. So essentially, if you have anything underneath one big square root, you want to break it up into a numerator and denominator and work on those separately. Just like in multiplication property, this works in reverse as well. You can combine radicals that are in numerator and denominator into one big fraction, and sometimes that will be useful as well. So let's do a few examples here. Let's take a look at the root 13 over 100. Again, it's a fraction underneath a square root. Can't have that, so we'll break it apart into two separate parts. Well, the top, it's a prime number. It's going to stay underneath the root. There's nothing we can do for the 13. But on the bottom we get a perfect square. Essentially, 100 is 10 squared. And in this case, we can cancel out the power of 2 and the root, or the square root. And when this happens, you get root 13 over 10. Now we're all good to go. It's no longer a fraction underneath a square root. It's been simplified as far as it can be. That's your answer. Now what if we had a problem like this? What if I told you to deal with this problem? 5 root 7. Sorry, square root of 5 over 7. Now it's a fraction underneath a square root. Just like before, you are going to separate them out so you no longer have a fraction underneath the square root. But if you remember, one of the things you can't have with radicals is a radical in the denominator. Now, unlike the case before where that 100 was a perfect square, That 7 is not a perfect square, it's a prime number. So there's nothing you can do to shake off its square root. And we can't have radicals or roots in the denominator. So how do we fix it? In a case like this, where you end up with a denominator that can't be simplified any further, you can multiply the entire fraction by another fraction that looks like this. Now why did I do this? Well, if you take a look at just that fraction, it's root 7 divided by root 7, which is technically just 1, because anything divided by itself is just 1. So mathematically speaking, it's as if I'm multiplying this fraction by just the 1. So I'm not changing the fraction in any way. This is essentially a 1. But what I do now, or what I can do, is I can cross multiply these and I get this. Now on the top, the product property allows me to recombine radicals, and I do that and I get root of 35. Again, nothing I can do there, that's going to stay as a square root. But on the bottom here, what I can do is combine them again and get a 49. Now that 7 was a prime number. That 49 is not. 49 is 7 squared. And as I told you, anything square root to the power of 2 can cancel out its roots. So the final answer to that problem was this. And we fixed it. We got rid of the root in the denominator. Yes, it made our numerator a bit more complicated, but that's fine, and we're okay with roots in the numerator. The whole point is to get rid of the root in the denominator. We accomplished this, we did this. Now, again, why am I multiplying it by this? So let's do another example here. Let's do square root of 2 over 3. Again, first step is break them up into separate roots because we don't like fractions underneath the square root. Once we do this though, we get a root in the denominator. Can't have roots in the denominator. So I'm going to multiply the first fraction by a second fraction that's composed of the numerator and denominator being the exact same thing as the denominator of the original fraction. Root 3, root 3. Because again, root 3 over root 3, that's a 1. Anything divided by itself is a 1. 2 over 2 equals to 1. 3 over 3 equals to 1. So root 3 over root 3, that's also a 1. So I'm not changing the fraction in any way when I multiply it by this. But again, what it allows me to do is when I cross multiply, I can get root 2 times root 3. That's not very interesting, but down here I get root 3 times root 3, which gives me a root 6 on the top. Can't do anything there, but on the bottom I get essentially root 9, which is a perfect square. And just like with every single perfect square, I can cancel out the power. And that's how I get rid of the denominator. That's how I get rid of the square root that's inside the denominator. You multiply it by a new fraction that's composed of entirely of whatever square root you're trying to get rid of. So it's composed of both numerator and denominator from that same square root. So that was the quotient property. Let's take a look at sums and differences. Now let's say I give you this particular problem. 4x plus y minus 9x. What can you do there? What does that equal to? Now you're probably wondering, what does this have to do with roots? So hold on just for a second, you'll see. Now if you have a problem like this, you know to combine your like terms, dx and dx, and the y doesn't have anything similar, so there's nothing you can do there. 4x minus 9x, that's going to be negative 5x plus y, and that's going to be the end of that problem. What if I gave you this problem? 4 root 10 minus root 13, sorry, plus root 13 and then minus 4, that's not a 4, that's a 9, sorry, so 9 root 10. So take a look at this problem. Whenever you have addition and subtraction with square roots, you can combine square roots or terms that have the same square root just like you can combine like terms in this problem here. So you can combine this, you can combine this, you can't combine this. 4 root 10 minus 9 root 10 is going to be negative 5 root 10. And then because you can't do anything to the root 13, it just ends up here. Very similar to what we did with this problem here. So you treat roots kind of like you treat variables. Anything with the same root you can combine. So let's do another example here. Let's do a problem like this. So if I give you, for example, 7 root 5 minus 3 root 2 plus 6 root 2 and then minus 4 root 5. So your first step would be to go ahead and look and find anything that has the same square root, kind of like if you were looking for anything with the same variable. So here I have root 5, root 5. Here I have root 2, root 2. And anything with the same square root you can combine kind of like you can combine like terms. So 7 root 5 minus 4 root 5, that yields me 3 root 5. Negative 3 root 2 plus 6 root 2 yields me with a positive 3 root 2, and that would be my answer. So just as simple as that. You treat the different roots as if they were variables. So anything with the same root you can combine. Anything with a different root you can't combine. And if I give you a problem, for example, like this, and just like with a variable here, just a side note, if I gave like something like root 5 without anything in front of it, you pretend that there is a 1. Just like with a variable, if it's just an x, you always pretend that there is a 1 in front of that. Same thing with the root. So if there is something without coefficient, there is a 1 there. Let's do one more example. What if I give you a problem like this? 5 root 3 plus 48. Well, right now they have different roots. You can't really combine them. But we can break this down. The 48 can be broken down to, right? The 48 can break down into 3 times 16. And as I already showed you, this 16 is a perfect square. It's this. And perfect squares can cancel out their roots. So that 4 goes on the outside, and well, you're left with a root of 3. If I bring this down, now I have a situation like this, and here I have the same root. So I can combine these like terms, which is 9 root 3. So again, you treat the different roots as if they were variables, and any of the same roots you can combine just like you can combine like terms. So thank you very much for watching.